We also have our secretary, Amanda, treasurer, Renzo, program committee chair, Uche, and communication chair, Samuel, our marketing chair, Anna, community affairs chair, Liuyan, and social and recreational chair, Laura, and our Plant City representative, Ayesha. And I also would like to acknowledge the generous support that we are receiving from our center director, Dr. Rex Siegel, and also from Kenneth Parker from the Florida Strawberry Growers Association. And also I would like to thank Plant Breeding Working Group and the Plant Science Council for working with us to make this event happen today. And if you want to know more about activities and projects that we are doing to help enhance the GCREC experience of our members, please visit our website. Thank you.
Okay, thanks everyone. I'm going to go ahead and introduce our speaker for today. Dr. Rex Bernardo is a renowned plant breeder and geneticist who was born and raised in the Philippines. He obtained his bachelor's degree in plant breeding at the Visayas State College of Agriculture in the Philippines, graduated with distinction, and then went on to work in a national plant breeding program for sweet potato. Like many of us here, his journey abroad began as a graduate student at the University of Illinois, where he pursued a PhD in plant breeding. Prior to joining the University of Minnesota, he was a research scientist at Lima Grain Genetics for 9 years and a faculty member at Purdue for another 4. Currently, he serves in various academic and leadership roles at the University of Minnesota, including professor and endowed chair in corn breeding and genetics. Throughout his career, Dr. Bernardo has made significant contributions to the field of plant breeding, including widely adopted methodologies in quantitative genetics and marker-assisted breeding. His work has been cited over 7,000 times, and he has authored 2 books that have become standard references for plant breeders across the globe. But I think I speak for all of us here when I say that what we cherish most about Dr. Rex is his enthusiasm, his commitment to making science accessible, his novel approaches that constantly challenge us and enrich our training as plant breeders, and his creativity, which is demonstrated in the title of his talk today, Plant Breeding When I Was Young, Now That I'm Older, and When I'm Dead. We're so glad to have you here with us today, so please help me welcome Dr. Rex Bernardo.
Well, thank you. Can you hear me, see me online? Should I move?
Yes, move. There you go. We can hear you and see you. Thank you.
All right. Can you hear me now, right? That old commercial. Well, it's a pleasure to be here. When I hear an introduction like that, it's like my life is flashing before my eyes, right? Oh, yeah. And it's a pleasure to be here. This is, for me, trips like this are exciting. And I would like to thank the organizers. First, I'd like to congratulate the group of graduate students and professionals. It's wonderful to be working together as a team here and enriching your experience here and helping each other out and learning skills that would last you a lifetime, whether you're here or whether you join another organization in the future. Also, thank you to Elisar for inviting me. She pushed all the right buttons when she sent me that email invitation. And I could not come, but really even before she invited me, the initial invitation, I go, wow, I've never been to this site. Vance and I are good friends over the years, starting from when Vance was a young graduate student at the University of Minnesota. And then I've worked with the Rose Breed group, and I've gotten to know people like Luis over here in Sujit. And so again, this is a wonderful opportunity for me to meet old friends, old colleagues from years past, as well as meet new people. And a young group like this always gives me excitement and enthusiasm for the future because I see a lot of promise in this room. And Elisar asked me to talk about 3 things. One is my journey, so to speak, as a professional in plant breeding. Second is some of the work that I've done over the years. And third is to speculate on what developments might be in the field of plant breeding in the years to come. And so hence the title for my talk, Plant Breeding When I Was Young, Now That I'm Older, and When I'm Dead, figuring the last part, if I make wrong speculations, I won't be around for you to needle me, and I can say anything and get away with it. And so I'd like this to be a fun session, so to speak. And later on, after this talk, for those in the room, we'll have a professional development session. I've got some gear here that I brought with me. I'm going to ask you to do things, and I think Cheryl's also already a bit scared of what I'm going to ask you to do, and that's okay. It's non-threatening. All right, and I'll be talking without slides. I'll just be talking like this. I've become quite lazy or creative, however you want to see it, over the years. And it actually started in Tampa during the crop science meeting. I was asked to give a talk, and a second talk, and a third talk during the same week. And it got to the point I go, I'm not going to make a third set of slides. And said, I'll just talk. And that went well. So I said, okay, I think I can try to do this sort of presentation and be a bit informal about it. So a little bit about my journey. I'm going to share some personal things. I mean, the science that we do, often you could read about those in journal articles. But the personal side, the science, the journey, so to speak, I mean, those you don't get to read about, right? And so that personal aspect is, for me, always nice to learn about from people who I look up to and respect. And so thanks for giving me the opportunity to do so. As was mentioned, I was born and raised in the Philippines. I got my undergraduate degree in the Philippines in 1983. And I started working with a sweet potato breeding program in 1983. And I go, wow, that's 40 years now that I've been working. And that's kind of a long time. And I think it's beginning to show, right? When you look at my hair, I should send you a newer picture. That photo in poster looks a lot younger than I look right now. But a lot has changed in those 40 years. So I came as a graduate student from the Philippines to the University of Illinois, met my wife at the University of Illinois, got married. My wife and I are blessed to have 6 F1 progeny, 3 boys, 3 girls, a perfect chi-square ratio if you run that test. And now I have 1 F2 progeny that's called a grandson. And this year, I have 2 more F2 progeny coming. And so it's an exciting season of life for my wife and me. And it's good to reflect on this and just the blessings that I've received over the years. And so, again, it's wonderful to take a step back and see one's path and where that has led and what the future might hold. And I'm going to phrase my talk about plant breeding based on its definition. We define plant breeding as the genetic improvement of plants for human benefit. Genetic improvement of plants for human benefit. I think that's a fairly concise definition. I'd like to structure my talk around the different parts of this definition of plant breeding. Genetic improvement of plants for human benefit. And then as I do so, looking a bit at the past, at the present, and then perhaps speculating on the future. Human benefit, let's talk about humans. When I started my career in plant breeding, the world population was 4.7 billion. 4.7 billion were living in this good earth when I started my career 40 years ago in plant breeding. Now, the latest figures were about 8 billion. And I think of that, wow, less than 5 billion to now 8 billion people. That's a huge number of people who have been added to our population. And if we speculate looking 40 years into the future, say 2063, the projections will be about 10 billion. And that's a lot of people, if you think about it, that's been added to this good world that we live in. And there's a lot more mouths to feed and a lot more demands on what we need to survive, not only survive and to flourish. And so the number of people obviously has grown over the last 40 years, and it'll continue to do so. Projections, though, are that it'll probably stabilize at around 10 billion or 11 billion in the centuries to come. Genetic improvement of plants for human benefit. We're improving plants not for the improvement of plants themselves, but for our own benefit. If we're interested in improving plants for the benefit of plants themselves, we would not be selecting for against seed shattering. For plants want to shatter. We as humans, we don't want. So it's good to keep in mind that what we're improving plants for. And these human benefits have been obvious to humanity since the ancient times. For example, an ancient writer of scripture wrote this poem in Psalm 104, thanking his God for the plants that this writer was enjoying. And this is what he wrote. He wrote in Psalm 104, he gives grass for the cattle and plants for humans to cultivate, bringing forth food from the earth, wine that gladdens the human heart, oil that makes their face shine, and bread that sustains the heart. And I think of that poetry and I go, wow, that is fantastic. Start with the first, grass for the cattle. Anybody had grass-fed Angus beef? Oh, that is delicious. That is delicious. If you think of you know, I know that some might be vegetarian, but if you enjoy meat, grass-fed cattle, oh, that is a delicacy. Melts in your mouth. I've been in a churrascaria in Brazil, and that was an incredible experience, but I should not, I should stay focused, right? I should stay focused. Food for humans to eat. Aren't you glad regarding the variety of foods that we eat? Haven't you thought about that? We take it for granted, don't we? I mean, it's possible that there could be, say, only 5 plants in the world, and that's all we eat. Oh, but no, there's a huge variety of plants that we eat. What if you had to eat only beans every day? Oh, your life would be miserable, right? No, we have beans, we have rice, we have tomatoes, we have strawberries, we have carrots, we have onions, we have coffee, we have chocolate. You think of this variety of foods that we have, it is mind-boggling. And why? It's because of the variety of plants that we can enjoy. And so it's really wonderful and inspiring for us to be working as plant scientists on such a wonderful, wonderful subject, just the variety that we see. And even talking about, you know, wine gladdens the human heart, just the enjoyment and the pleasure it gives us. It's not just for our sustenance, but it's for our pleasure. Or the bread that sustains our hearts. And I even didn't think about this, oil to make our faces shine. I didn't even think of cosmetics because I don't do that, right? But yes, that's an important part too. So the point being that we improve plants for human benefit. And these human benefits currently are food, fiber, food, feed, fiber, if you think of clothing or the lumber that we get or for build houses. It's for fuel. It's for fun. If we think of fun, meaning flowers, the grass, the turf grass in golf courses and so forth. So again, it meets a myriad of human benefits. And moving forward in the future, it's interesting to speculate on what these human benefits might be. And even now we think of the different new benefits to humans that we might not have thought about. Now, Vance might remember this from my plant breeding class that I taught that he took years ago. But the toughest crop I've ever pollinated, coconut. Oh, if you are a coconut breeder, I so admire you. Why? That coconuts are a pain to pollinate. For example, the way we pollinated coconut in the Philippines is, number one, we did not have access to ladders, okay? And so what happened was, well, people who came before us, they would hack these wedges on the side of the tree. And then you, as a pollinator, would have to put the bags on your back, and you would have to shimmy up the tree on these wedges, you know, like a human Spider-Man, so to speak. And then you sit on that big leaf, and you need both hands, so you need to be secure. And you basically got your pollinating supplies and did your coconut coconut pollination, and then you climb down. Well, it didn't all flower at the same time. So if you're a coconut breeder, you had to do that, several times. And I'm sure you got good at it. But not only pollination, but even harvesting. The way it was harvested, people would go up, would climb up and just, chop the fruit until they fall down. And I'm thinking, wow, convenience should be a breeding objective. Convenience. And that's something we don't think too much about. Convenience as a breeding objective. How convenient might it be if a coconut breeder would breed the plant so that there's a good abscission layer that is formed at a certain time. And when the time is right, that just drops to the ground. Oh, coconut production would be a lot easier. And so I think moving into the future, even little things like this, convenience, I think would become increasingly important. I mean, you think of these cuties, these little mandarins, right? Why are they popular? Well, they look nice, but I think part of their popularity is convenience. They're so easy to peel, right? They're so easy to peel compared to say that your orange, that's quite harder to peel. And so we can think into the future and speculate that because we live in a fast-paced urban kind of increasingly urbanized kind of society, that these convenience aspects of the plants that we produce, either from a consumer's perspective or a producer's perspective, or even a processor's perspective, would become increasingly important. You think of processing of melon, for example. Have you thought about the size of that cavity that is needed? Guess what? That's an important trait that we might not necessarily be interested in, but the size of that cavity, the smaller that is, the better it is. So in a way, yes, that affects yield, but it's also a convenience trait because it makes cutting or chopping that melon or cantaloupe a lot easier than it would be otherwise. We could think of ecological services that benefits as benefits as well. When I started my career, we hardly thought of the ecological benefits that a plant might bring, or breeding plants specifically for increased ecological benefits. At the University of Minnesota, there's a huge breeding effort right now, for example, on cover crops. Why? You might not have it in a place like Florida, but in Minnesota, for much of the year, the ground is bare. Why is that? Well, we can plant in May, and we would need to harvest by September or so before the frost comes in. And then year-round in the spring, after the snow melts, that is bare ground that's subject to erosion and soil loss. So there's a huge breeding effort right now for different kinds of cover crops that then would provide these ecological services that we are seeking in the upper Midwest, specifically where the Mississippi or the bodies of water that feed the Mississippi come into play. So again, I think looking into the future, just these types of traits that go beyond the basic necessities of food, feed, fuel, fiber, and fun, I think I would speculate that those would be increasingly important. There could be fun examples. Have you heard of square watermelon? Yeah, some of you have heard of square watermelon. Right now, I think why would you like square watermelon? Well, for one thing, I think they're easier to put in the refrigerator, right? And they don't roll around and roll over your eggs. Square watermelon, I think that's being done right now just by making the fruit grow in a certain container. But what if you could do that genetically? I don't know how that's going to happen, if there are any genes that affect fruit shape that would actually make it a square. I'm hard-pressed to think of a squarish or cubic kind of fruit. But again, the point being that human benefits are all varied. And we need to think of these kinds of human benefits that might be present in the future more so than now. Genetic improvement of plants. And we think of the different plants that we work with. To me, it's very interesting because of the value of plants that humans, when they have migrated, they bring their useful plants along with them, don't they? In fact, one way of tracing the lineage or the domestication or the movement of different plants is by linguistics, because the plants move And the name, the native name of that plant also comes along with that. And just by studying linguistics, you can, for many species, you could see where that plant might have moved from. And it's not uncommon that a plant might find a better new home. I met somebody from Argentina. Hey, Malbec wine. Malbec wine, not native to Argentina, came from France in the southern region, but was introduced and found a better home, changed the name as Malbec in Argentina. We think of soybean in the United States. Back in 1924, about a century ago, soybean was grown on only 0.6 million hectares in the US. Today, soybean is grown in about 35 million hectares in the US. So think about this magnificent crop that grew from 0.6 million hectares to 35 million hectares. I mean, that's a huge increase. And why? Well, because soybean has much value for its oil, its meal, its protein. And I think as we look into the future, the main staples will remain, but I would like to think that there will be more breeding efforts in a wider variety of different plant species. There'll still always be orphan crops, but for me, it's exciting to even begin to see efforts to breed different species, particularly species that are culturally relevant. And I'll tell you about an effort we have at the University of Minnesota. I'm looking around this room, having met students. Many of you come from, you were not born here, wasn't born here, and you came, it was shown, I don't know how many countries, 20 countries around the world. And to me, it's always interesting how the foods from the home, from your place of birth where you grew up, all those trigger just the most wonderful emotional reaction in you. You miss those foods. You would like to have those foods. And oftentimes, we might not have easy access to those foods. So in where I work in Minneapolis, St. Paul, there's a huge immigrant community of people from Africa, East Africa, as well as West Africa. We have a lot of people who have immigrated from Somalia, for example, from Kenya, and from Ethiopia. And I found in this Minnesota Public Radio article a while back, okay, there's another group of immigrants in the Twin Cities, Minneapolis, St. Paul, who are well known in the community as producers of fruit and vegetables. They are the Hmong community. They immigrated from Laos and Cambodia, that area of the world. And they've started growing these African vegetables. And guess what? I read that people from Seattle would drive to Minneapolis. People from Houston would drive to Minneapolis just to buy African produce. And I'm thinking, oh my goodness, such is the draw, right, of these foods native to their homelands, that they would drive from Seattle or from Houston or from some other, Oklahoma or other some far-flung places to Minnesota just to buy their native African vegetables. And when the Plant Breeding Center, which I direct, was formed, I thought it'd be a nice student project to have a student-run vegetable breeding program that focuses on African leafy vegetables. And the idea is we want to focus on African leafy vegetables because they're best consumed fresh. We figured, okay, if it's cowpea or peanut that's consumed dried, well, might not be the same, but you could grow it elsewhere and ship it, right, in its dried state. But fresh leafy vegetables are best eaten fresh, obviously. And so now we have this fledgling effort on breeding African leafy vegetables. And it's been a fun effort because when we started these breeding programs, we didn't know what these vegetables looked like. We didn't know how they were consumed. We didn't know their ploidy level. Are they self-pollinated? Are they cross-pollinated? We knew nothing. And now we're we're starting to begin the breeding efforts. We'll be making some crosses. And this year I decided, hey, we don't have enough genetic variation. Executing materials transfer agreements is a bit hard. Let's try mutation breeding. And so that's what we're doing. We're zapping it with fast neutrons in the next week and just seeing what variation we'll get. The point being that with a movement of people and an increasingly urban and cosmopolitan and community, you know, I'd like to see more of these efforts in breeding culturally relevant foods. And we hope that the learnings that we have in this program would be useful as models for other breeding programs. Perhaps you can start one here at the University of Florida, as if you weren't busy enough, but right. But it's a fun breeding effort. And so genetic improvement, talk about plants, we talked about humans, we talked about benefit. The phrase genetic improvement also implies that there's non-genetic improvement. Okay, so we can improve crop productivity by changing the genetics and by changing the environments. And I didn't have this slide with me, but in my class, I showed a slide with 3 lines of genetic gains from 3 different species. One was fairly flat, one was in the middle, and then one was just really way high. And I told my class, one of this is for wheat, one of this is for corn, and one is for potato. Guess which one is which? And the most common guess is that for the line that went straight up, they go, oh, that's got to be corn. Because we're used to these corn breeders showing us these graph with just go to the high slope like this. And I had to tell them, no, that's not quite right. That's actually potato. If you think of the increase in productivity for potato, it's really, really steep. Corn is nothing, the gain. Well, actually, much of that is not genetic gain for potato because much of the production remains with Russet Burbank. It's more with fertilizers and inputs that have improved that level of potato productivity. So that being said, yes, we can improve productivity by changing the environment, which will become a challenge with climate change and decreasing inputs. But we as plant scientists, as plant breeders, we focus more on the genetic improvement of plants for human benefit. When I was young, plant breeding was so simple. Classes were easy. Plant breeding was simple. What? You crossed good by good. All the selection was by phenotype. And then you developed progeny, you selected the best, and you repeated that process. It's like, oh, this is fun. You just went to the field, looked at the plants, took notes, got the data, and that was it. Only one selection decision per year, so to speak. And those who have taken my course have heard this story, but my life changed in 1987 when a graduate student who was from Spain, who was studying molecular genetics, walked into our office of corn quantitative genetics and started talking about restriction fragment length polymorphisms, RFLPs, which I know you've never done before, but you might have heard about RFLPs. And we were going, what is this new thingamajig that you're talking about? Oh, they said, oh, remember these isozymes that we were looking into, protein markers? Now we have RFLPs, DNA markers that are cheap and they're more abundant. When I say cheap, yeah, well, not quite cheap. They're still expensive back then. But only $5 a data point. And we can get quite a few. We can get, 50 markers in corn compared to 12 or so isozyme markers. And we go, wow, that's a lot of progress there. We're increasing the numbers by a lot. That's a lot of markers, 50 in corn. And the technology was new. And I remember my first exposure to RFLP work was when my advisor told us, wasn't email back then. I'm trying to recall how he told us. I think he just told us on the phone. Actually, I think he actually picked up the phone and gave us each a call. Hey, come to the field on this day. We're going to collect DNA samples for RFLP analysis. I had a co-graduate student, RFLPs were new. He was studying this population that would be genotyped with 33 RFLP markers, right? 33, wow, that's great. So we went to the field. I see, this was a time before the smartphones. We should have taken a video back then. It would have been a lot of fun viewing today. But we were given these instructions. Rex, wear gloves. We don't want your DNA to contaminate the corn DNA. Okay, so war gloves. Here's a pair of scissors. Okay, what do I do with the pair of scissors? Well, you need to cut corn leaves about a foot long, maybe 3 or 4 of them. So yeah, don't be afraid, just cut the plants, just be careful, don't kill the plant, but that's what you do, you cut it. So we were doing that. And we were told, okay, put it in this mesh bag, and then put that mesh bag in a cooler. So that's what we were doing all afternoon. Of course, today, you know, you have, hey, seed chipping or even leaf punches. Hey, leaf punches are light years ahead of the procedure we had, more so seed chipping, but that was the procedure back then. And so after the leaf samples were collected, it was whisked right away to the local airport in Champaign, Illinois, where there was a private chartered airplane waiting to take this precious styrofoam container to a lab in Slater, Iowa. And that's what happened. Plane flew. Those were our precious leaf samples, population of corn to be analyzed with 33 RFLP markers. And I go, oh my goodness, this is an expensive undertaking if you need to charter a plane. But my advisor, John Dudley, really wise man. I'm so grateful that he took a chance on me and took me as a grad student, because I came from a not well-known school in the Philippines, but he took me on as a grad student. They gave me a chance. He said, Rex, here's how you think of it. Don't think of it, think of applications of molecular markers, not how they are right now, but when they become as expensive or as cheap as a paper clip that we use to pollinate corn, our pollinating bags, we need to put a paper clip. And I go, that's pretty far-fetched. Will that ever happen? Guess what? We're beyond that. I checked on the price of a SNP marker. These days, it's about 0.2, 0.1, 0.3 cents per data point. The cost of a paper clip, it's about 0.7, 0.8 cents per paper clip. So that has come true. And so I guess looking ahead, that's a lesson for us here. You have a long career ahead of you, and you need to potentially think of technologies not necessarily the way they are now, but how they might be in the future. Because technologies, as we know, they change so very quickly. Think of AI, which I'll discuss later on. Think of artificial intelligence and how that has changed so quickly. But again, that was my first lesson, so to speak, in restriction exposure to molecular markers. And so the presence of molecular markers in my career opened up this entire avenue of possible research and research applications. Because now, okay, we don't have to rely on phenotypic data anymore, or not solely on phenotypic data, but now we have another tool, DNA fingerprints, that we can use in the breeding work that we do. So much of my research over the past several decades, as you might know, has focused on the use of cheap and abundant DNA markers in plant breeding. My initial use of DNA markers was trying to predict hybrid performance. I was working with a company, Limagrain Genetics, that now is known as AgReliant in a joint venture with KWS, a German company. I worked with Limagrain Genetics right after graduation. I was looking for a postdoc. To be quite frankly, it was my backup job, but I'm so glad I took it, because it could not have turned out better, because it afforded a wonderful opportunity for me to grow as a researcher. So back then, the company was interested in trying to predict hybrid performance. The idea being that, well, in corn, we grow single cross hybrids. And if I have 100 potential parents from one group and 80 potential parents from another group, 100 times 80, that's 8,000 potential single cross hybrids. And we did not have the resources to test all 8,000. We could test maybe 10% or 15% of that. That's all we could do. And so if you have a combination that was never tested, there's no chance of that be able to become a hybrid variety later on. And how were the breeders doing it? Well, just by looking at things like general combining ability or intuition, really. Oh, I think I should cross this one with this one. And so still remember pacing the room when the moment came to me. Oh, this prediction business is just like how animal breeders predict the milk yield of a dairy bull that I learned in school. A dairy bull obviously does not produce any milk, but it has good genes that it can, or bad genes that can pass on to its progeny that affect milk performance. And so how is that done? Well, you look at the female relatives of that dairy bull, you look at the milk records of the female relatives, you use that information weighted appropriately according to how closely related that female relative is to the bull. The mother is more closely related than the half-sister, so you put more emphasis on the milk production of that mother. And I said, oh, this is just like this problem in hybrid prediction I'm working on. So the bulls could be the hybrids that are not tested. The female relatives, those would be the hybrids that have information. And it's in hindsight, I said, oh, this is a fairly straightforward prediction problem. Now, at that time, we did not have very good pedigree records for some of the individuals. And so I said, well, because of the lack of pedigree records, I could estimate relatedness just by molecular markers. So that's what I did. I used the traditional, so to speak, best linear unbiased prediction, BLUP approach, and estimated relatedness based on molecular markers. And that has what has become now known as GBLUP, genomic best linear unbiased prediction, which it turns out, I think, is the most widely used genetic evaluation method in the animal breeding world. I didn't think of calling it any name back then. I said, well, you know, it's really a straightforward application. In fact, one of the reviewers of that Bernardo 1994 paper said, I don't know if this should be published. I mean, what did you do? You used molecular markers to estimate relatedness and predict hybrid yield. So, you know, what's the big deal? Well, I said, it hasn't been done before, and I think it has value that breeders would appreciate knowing about this methodology. So I'm glad that the editor eventually accepted that paper. But if you sum my work over the last several decades, I can sum it in one word, and that is prediction. I've been interested in prediction in different aspects, either predicting hybrid performance, either predicting the performance of individual seedlings, what their yield would be. And I must say it was sometimes uncomfortable during those days, sometimes embarrassing, because I kept using this word prediction in the articles I wrote. And it seemed that nobody else was doing that at that time. So I'm very glad right now that, hey, it's a commonplace now in the plant breeding literature, right? You read a journal article, oh, prediction, that's something we do routinely. Even something like best linear unbiased prediction or BLUP. To me, that was new back then. I didn't learn it in school. After my graduate school, I came from my professor said, Rex, to the extent possible, avoid unbalanced data. Because unbalanced data, oh, they're just messy. So you want your data to be just as balanced as possible, and then you just calculate the means, least squares means, and so forth. And you know, that worked fine for a thesis experiment. But when I got to the plant breeding world, like, oh, wow, most of my data actually are unbalanced. And then tools like mixed model analysis, oh, they have a great important place now in the work that we do. Those predictions today dwarf whatever initial predictions that were made that I did in 1994. And a big part of that was, number one, the availability of specialized algorithms to do these predictions. And number two, even just bigger and faster and cheap computers. The first GBLUP predictions were done on a Pentium 90 machine with 64 megabytes of RAM. Okay, 64 meg. And now, of course, 64 gig. I mean, that's fairly common, right? But at that time, the memory in the PCs, personal computers, the usual memory was about 4 or 8 megabytes of RAM. And I still recall that time when I dialed my phone to place an order for a computer. No Amazon back then, right? I had to place my order for a computer by calling somebody on the phone. And I said, I'd like to buy a computer with 64 meg of RAM. And there was silence for a few seconds on the other end. And then she said, what do you need 64 meg of RAM for? And I had to explain, well, I'm doing these, scientific computations. I'm storing large amounts of data, 2000 by 2000 matrix in double precision. That takes up quite a bit of RAM. I didn't go to that detail. Finally, I got my machine. But again, it's this availability of machines these days that can facilitate the work that we do. And it goes back to, again, my earlier point. You're at the stage of your career when you don't know what the technology might bring in the future. And don't be limited in your thinking don't be limited in current technological limits, because that would change. And it might not be RAM, it might not be computers, it might be something else. It could be ground sonar to look at the roots of plants, or maybe little robots that would dig through the soil and take measurements of the plants. So you think that's possible? Like, I see nodding heads. I like that. Yeah, why not? If you want something done, tell an engineer it could not be done. Okay? Tell an engineer, no, this could not be done. And the engineer would take that as a challenge and maybe develop something for you to use. Now, as I look back at my career, and I've published a paper on this, there have been different bandwagons, so to speak, that have come and gone. Bandwagon is something that becomes increasingly popular as more people adopt it or jump onto it. And then it ceases to be a bandwagon when it becomes part of mainstream thinking, or when the non-useful parts of that bandwagon are discarded. And in my career, I've seen many bandwagons. Before my time in the 1930s, 50s, the bandwagons were mutation breeding. Polyploidy was a big bandwagon. People were saying, oh, we could make grapes this big, by polyploidy. Quantitative genetics, in a way, was a big bandwagon in the 1960s. Tissue culture was a bandwagon in the 1970s. And what bandwagon might have a bad connotation, but actually some bandwagons are useful. If you think of hybrid corn was a bandwagon in the 1920s. It was new, it was novel, it was revolutionary, but then people saw the value of hybrid corn and nobody talks about it as a bandwagon anymore. And so when we think of the state of the art today, we have different things that have come up. There was QTL mapping. There was a big emphasis in the 1990s. We have learned much. We have learned much about what doesn't work. We have learned about what works. I think now we have best practices on what to do. We wasted is too strong a word, but yes, spent a lot of money on that effort, published a lot of articles on QTL mapping, pointing to myself here as well. But now I think we've come to that point in plant breeding. Basically, what you want to do is focus on major QTL. Then, after that era of QTL mapping, came that era of using genome-wide markers to predict performance. And I know that there's been a lot of work on genomic prediction here at the University of Florida, and continues to be an emphasis right now of the work that is being done. If I try to summarize the state of the art, or try to summarize what we've learned from genomic prediction, number one, it works. Okay. Sometimes it works really well. Sometimes it doesn't work at all. On average, if you use it routinely and judiciously, it works. Just like phenotypic selection. On average, phenotypic selection works. Sometimes it works really, really well. Sometimes it doesn't work. When it doesn't work, you don't worry too much about it. You just move on. Use it in your program. And I think we're come to that point in genome-wide prediction, at least major breeding organizations in corn and soybean. It's used routinely. You know it works. It works sometimes really well, sometimes not as well. Number two, there are many factors that affect prediction accuracy. For me, the number one is relatedness. If you can maximize relatedness between your training population and your test population, prediction accuracy is maximized. Should be no surprise, coming back to my dairy bull example, if the females are closely related to the bull, you should expect good prediction accuracy. If they're not related at all, then the prediction accuracy should be low. So that should not be any surprise at all. So I think, those are the main learnings. And now you think of, well, what is to come next? And we have seen many things, many technologies that are here. Transgenics is one of them. And now there has been phenomics work that is being done, development of drones, development of robots, and so forth. I'm not into that field. As I mentioned, what I'd really like to see work being done in the future, perhaps when I'm dead, is just measurements underground. If we can do that, if we can have underground drones of some sort, I think that would be a really useful advance. And now we have genome editing as well. That again, I think there's great potential for genome editing, but we need to have good information actually on the genes, I believe, that we want to edit. Otherwise, we're back to kind of like plain old mutation breeding. When I speculate on what breeding might look like in the future, it harkens back to an illustration that I've used on car design and car manufacturing. If a plant breeder were to design a car, or if a car engineer were to design a car the way a plant breeder works, this is what the car engineer would do. He or she would take two high-performance cars, a Porsche and a Ferrari, shuffle the different parts together, engine from the Porsche, transmission from the Ferrari, come up with a mosaic of a car, and then choose the best ones and repeat that process again. So you have this shuffling kind of approach rather than a design kind of approach in plant breeding, right? Meaning that there are many aspects of the plant breeding program that we can control. We can control which parents to cross. We can control how the progeny are evaluated. But so far, we've been putting ourselves at the mercy of meiosis, recombination, as well as the formation of zygotes. And I'm beginning to think, well, are there ways to have a better control over that? Okay, so that a piece of area of research that I'm doing on right now that you might have read about or familiar with is what is called as targeted recombination. Targeted recombination refers to having recombination events at those places or marker intervals where you as a breeder think they would be most beneficial. And the recombinations could be either natural, meaning you select for natural recombinations and you try to pyramid them, or there's a possibility that I'm hopeful it'll be beyond my career that actually could be done perhaps artificially. Meaning that with CRISPR systems, so see what CRISPR does is it makes double stranded cuts in the genome, right? And so what CRISPR does is instead of genome editing, you could view it as a tool to induce recombination in somatic cells. So that if you say, okay, I want a recombination between marker 25 and 26, you could design CRISPR to make that cut there and induce recombination. And do it in a multiplex kind of way to have, so that you could have the recombinations you want. And I think of this then as then moving plant breeding from less and less of, well, let's just toss the genes together in a random fashion, so to speak. But now seeking to have greater control over that recombination process, because as you know, recombination is the magic sauce, is the, so to speak, that gives us what we would want. So as we look into the future, I have one last piece of advice for the graduate students here. Continue to be learners. You're learning right now, and you need to adapt this lifelong aptitude and attitude of being learners. My former professor, John Dudley, had this poem, I guess, in his office. I forget the name, it escapes me right now who said this. But it's how it went. In times of change, learners inherit the earth, but the learned find themselves beautifully equipped to deal with a world that no longer exists. If you consider yourself as learned and having learned everything, things around you would change and you would find yourself equipped to deal with the world yesterday. No longer exists, right? But you and I need to be continuous learners and try to keep on learning new things that would help us function and do well as scientists in our chosen vocation in an ever-changing world. And if you think of the changes right now in the field of plant improvement, a lot of these changes happen a bit on the periphery. And when I say that, technology is not necessarily designed for plant breeding by itself, but technologies that were designed in other fields, but that could be applied to what we're doing. Just to give an example, I'm teaching a class called Professional Skills for Scientists at the University of Minnesota this semester. And just yesterday, I was teaching a class, it used to be on email and memos. Okay, if I write an email, what are some best practices? We have exercises actually in writing emails and even writing the subject heading of an email. How do you do that? What's front loading and that sort of thing. But I had to change the memos part. Now it was emails and ChatGPT. Why? Because I've heard of the tool. And at first I was hesitant. You know, I'm an old school kind of guy. Guess what? I even program in Fortran. Well, it's Fortran, it's a computer language that's no longer taught in schools, but it's the one language that's sent men to the moon. I had a flip phone not too long ago, but that's another story. But I tried ChatGPT and I asked it, write a paragraph on why scientists need to learn professional skills. I didn't say how long the paragraph would be, but it came out with this beautifully written paragraph. And I go, oh my goodness, what a tool. And I'm thinking, okay, I have this technology. It's either as a professor, I say, no, not gonna touch that. It's gonna make my students dumb. It's gonna make them say, write me a 15-page term paper on genomics and plant breeding. You could do that, right? Or you could say, wow, here's a tool. There's a lot of potential. How do I use it? How do I best use it in the work that I'm doing? And my student, after the session, one of my students, she said, I'm writing this thesis proposal and I'm trying to, improve the introduction. I have a good draft. Is it okay with you if I use ChatGPT to try to improve it? So yes, go ahead and do so. I mean, if you were coming from, hey, can I use ChatGPT to write the entire introduction? I would say, maybe no, maybe no. But now you have something, you use this as a tool. It's like an editor, right? And so again, just an example, we have these new technologies coming around us. And I think we should not be afraid to test them and to use what is useful, but discard what we don't think is useful. And part of that is continuing to be a learner. If I think of a career as a scientist, there's a life cycle of a scientist. Did you know that? A life cycle of a scientist is as follows, or a professional for that matter. In the first stage of your life cycle as a scientist, you learn from others, you depend on others. You're learning from your professor, you're learning from colleagues, you're learning from postdocs. Second is when you begin to contribute independently, okay? You now become a PI, an assistant professor. You become a USDA GS13 level scientist. You have your own program, and you're beginning to contribute independently. A third phase is when you contribute through others. When you now, as a professor or a PI, you now have grad students, you have postdocs, and a lot of your contributions are through the contributions of other people that you're working with. And the fourth stage that not everybody goes through, but some people do, is institutional leadership. It's when you look at the broader organization, and it could be a formal role or an informal role, and you begin to think to yourself, okay, I've had my career, and now I'm in this stage where I think my career would be most meaningful and measured in terms of what leadership, formal or informal, do I bring to my institution. I find myself in that last stage right now, where I'm beginning to provide institutional leadership to where I am. But what you would see is through all of these stages, learning continues to be important. You learn about science at the start. You learn through that. As you progress through your career, you begin to think, oh, yes, I learned about science, but now I need to learn more about professional skills and working with people. And so whatever it is, learning should be a hallmark of each of our careers. And so I leave you with that piece of advice. You're learners, keep learning, don't stop learning. Don't stop learning whatever it is. Be it plant breeding, be it cooking, be it a new dance, whatever it is, be a learner. It serves you well in the long run. So with that, thank you so much for having me. I purposely left enough time for questions, but thank you for being a wonderful audience. It's a delight, again, to be here with you. It's my pleasure and honor to speak with you today. Thank you.
And then go to Zoom and do the questions. So we can start in the
Rex, thanks for the talk again. It was great to see the whole span of your professional life being laid out a bit, and I would love to relate another question to you. So you talked about gene editing, for example, and also genetic improvements of plants to serve human, benefits. What do you think from a consumer side, which would be important to address? And I'm thinking about companies like Pairwise, for example, that look at classrooms, what the kids bring to their lunches, and they think about gene editing to improve quality of food that should be more involved in our daily lives, thinking about food quality rather than quantity. Mm-hmm. What's your take on that?
Well, my take on that, thank you for that question. So my take on that is that we as plant scientists need to do a better job at communication. I think many of the questions we get, or many of the pushback we get, would be from a lack of a proper understanding of what really is on hand. Let me tell you something, just an experience I had. I had a friend, she's an influencer on TikTok, and she's into organic foods and healthful foods, and that's great. And she told me, Rex, I don't get it because I go and buy my frozen sweet corn at my local grocery store. It says non-GMO, and then I read on the web, it says, wow, 90%, more than 90% of the corn crop is genetically modified. So are the companies like Green Giant, are they deceiving me and saying their sweet corn is non-GMO, where I read from the USDA that 90% is GM? And so I had to explain to her, well, okay, there's sweet corn, and then there's field corn, and they're different. And 90% of the field corn plus is GM, and sweet corn not necessarily so. But to her, corn was corn. She did not appreciate the fact that, the sweet corn I have is different. And so for me, a big part, whatever it is, gene editing, nutrition, whatever it is, a big part of our challenge is communication and education. And where I land is, if you decide to consume only organic produce, I have no problem personally whatsoever with that. That's your choice. no problem for me whatsoever. Or if you want to consume only non-gene edited food, if and when that time comes, I have no problem with that. However, I think it's important that you understand what exactly you're talking about. Don't tell me that, oh, okay, this is genetically modified, and just begin to think of whatever kinds of things that would come to mind when you talk about genetic modification. For example, I'm on TikTok actually through that segment, but I've never seen it. But my student told me he saw me on TikTok, and I go, I don't even want to see what it looks like. But I had to explain to my friend. So yeah, basically a lot of the corn is genetically modified. And guess what the scientists did? They just borrowed a mechanism that's naturally occurring in bacteria. There's this bacterium that inserts its own DNA in plants already. And what scientists did was simply use that bacterium, made a few changes, and inserted this DNA that they want. So we're just piggybacking on a natural process. So she was appreciative, she was receptive, but again, I think in many of the issues that we're dealing with, it starts from, number one, a lack of understanding. And then for me, again, it's respecting choices. If that's what you decide, great, but don't necessarily impose your choice, your personal decision, your personal choice on others. I mean, make that available, but don't necessarily impose it. And yeah, we live in such a divided society, and social media just makes that, what I just said, even more difficult. Because what? Hey, it's on the web. It's got to be true, right? So later on in the professional skill session that I'm actually leading, there'll be two sessions. One is on team building. The second one is actually on communication.
Great stuff learning today. So about prediction in the future, you say it might increase, right? That's what I got from the talk. Do you think phenotypic measurements will increase in the field, or they will stay the same, or will be more prediction to complement phenotypic selection with genotypic selection?
Thank you. The way things are now, obviously you can't get rid completely of phenotyping, because the way we're doing things, we're using markers as a surrogate for the phenotype. And so we still need that good base of phenotypic data. And in fact, I think that's one of the challenges today that we're facing is if a program shifts heavily to prediction-based breeding and then begins to phenotype only a portion of what they would have otherwise phenotyped, then future predictions would rely only in that portion. And we've shown that doing so actually decreases the effectiveness of future predictions. So there needs to be some form of phenotyping that is done as an investment for the sustainability of future predictions. So one easy way to do that is, well, yes, you select the best, but you also select a few of the worst ones. And we've shown that when you do that, you select the best, but also purposefully select a few of the worst ones, and you phenotype those. Having the worst there adds a lot to the accuracy of future predictions. From a practical perspective, it also serves as a control. Because if I predict these to be the best, I predict these to be the worst, I grow it in the field next year. Oh, guess what? They're the same. Then that's a red flag. Oh, maybe either my phenotyping isn't quite right or my predictions aren't quite right. But yes, that's something well worth thinking about as you begin to apply this technology in breeding.
So while you were speaking about your career, I remembered something that I read on something. A lot of research effectiveness is tied to emotional regulation, and because there's obviously an infinite amount of research that you can parse through and then maybe not get anything done. So just getting over that, paralysis, being overwhelmed by everything that's available, especially that you're now inviting us to go beyond just the fields of plant breeding. So I have two questions. First, I would like to hear your insight about the emotional regulation side. And then the other thing is, after, lifetime in research, have you developed any mental filters to what technologies or what areas are have potential and are worth learning about, or things that maybe because they're not reproducible or convenient, as you were saying, are just not?
All right, well, thank you. Let me try to answer the different parts of your question, Elisar. About that emotional trigger. Yes, emotions do play a huge role in the work that we do. And we'd like to think of us as pretty emotionally detached scientists. That's not true. Okay, you and I have emotions. I mentioned our work on the African leafy vegetables. Oh, that brings a lot of emotion to us as scientists, also actually also to the growers the African immigrant growers who would visit our field. Much of our work has been building bridges with them. A lot of emotion involved in that. And I say emotion, positive emotion. And that's why and I'll mention this for the audience on Zoom who cannot join the professional skills workshop. But one thing, tell stories. Did you notice how many stories I told you today? I told quite a few stories. Why? Because that connects with the emotions that we have. And the stories we tend to remember more than facts and figures. All right? So I challenged my class actually to think of stories to describe their current research. And one raised her hand. She works in Africa and in Alaska. And her story was, oh, there was this big layer of organic matter. And to cut it, they could not use their usual tool. They had to use a bread knife, cut through about a yard or so of organic matter. And I said, oh, excellent job. Next time I see a bread knife, I'm going to remember you. And so again, stories connect. They're an effective way of communication. As far as filters, I saw you did StrengthsFinder, right? We do StrengthsFinder as well. My top 5 strength profiles are strategic, belief, learner, responsibility, ideation. So my top one is strategic, and when I see something, my mind immediately goes to, okay, will this be applicable in a real world breeding program? And if I see that it's not applicable, my mind shuts off right away. I'm going, okay, I'm not going there. If I see it's applicable, then to me, that is more interesting, which has been to my detriment professionally. Why? Because there are a lot of calls for funding, right? And when I look at the request for application, I go, okay, this can bring me money, but I'm not really that interested in this topic, or I don't see how it might apply in the long run, and I don't end up applying for the grant. And my department is telling Rex, we need to submit grants that produce indirect costs that would support our department in college. So that's a weakness that I have. And yes, I am asking you to be learners, but actually that's a lot easier said than done because of the proliferation of the field. If you think about it, well, what do you need to learn today? When I was a grad student, yeah, you learned phenotypic selection. You learned statistics. Molecular genetics, a little bit, kind of token at that time. But now you're being asked, okay, you need to learn statistics. You might need to take a machine learning course. I was at a convention, an annual meeting in Chicago about 2 years ago. And I posed this question because the session was on education. And I said, what new fields should we be teaching our students? And the answers came in very rapidly. Yeah, we need to teach them professional skills. We need to teach them machine learning, molecular genetics. That's important. I posed a follow-up question. We only have a certain number of credits in our breeding program. What should we take out? 0 answers. 0 answers. It's like keep adding, but that's in a way that's impossible, right? In a graduate career or curriculum with a fixed number of credits, if you add something, or something has to go out, and that's a tough question, and I don't have easy answers. Take out quantitative genetics. I'm a bit serious. not the whole thing, but take out some of the quantitative genetics that we might not need as much anymore. Maybe that's one part of the answer. Let's moderate.
We have a couple questions on chat.
Yes.
I might read them. So the first one we had was here it is. You mentioned 3 topics in your talk: family, career, and active learning. Do you have any advice on how to balance the 3? And thank you for your talk, the comment says. The other question, if I may read the 3 of them, says, do we have a saturation point for breeding / improving crop species? How should we look at this aspect? And the last question was, did it ever cross your mind to go back to the Philippines after your graduate studies?
All right. Let me try to answer the questions. I might need a prompt again if I forget. I tend to forget things now these days. So, work, life, family life, learning. Yes, 6 kids. My wife was busy. We homeschooled. She was the head teacher. I was the principal. Principal didn't do too much, right? It was mainly the head teacher. I actually tried to calculate how many diapers I've changed in my life. It was like 10 or 12,000, some humongous number now in the landfills, right? But I digress. Work-life balance, you've heard of this term. How do you define work-life balance? My definition of that is achieving success and enjoyment in my work and outside of work. That's how my personal definition. For me, I can have what you call work-life balance if I can achieve both success and enjoyment in my work and outside of work. And guess what that first word is? It's achieve. It doesn't just happen, right? It's something you need to work hard at. Well, number one, working hard at it means you make choices. You make deliberate choices as to according to your values of what is important to you and what is less important to you. Early in my career, I made a choice. I value my job. I value the job for what it brings, for the income it brings to support my family. But I said, I don't want to be defined as a person by my job. That's not me. I don't want to be that, right? When you think of Rex, I want to friends and people think, yes, he's a plant breeder at the University of Minnesota, but he's also beyond that, right? So number one, didn't want to be defined by my job. I wanted to put limits then to the time that I would be spending at work or the amount of time that I'd be, doing emails at home when my kids were young. You make deliberate choices knowing that those choices have consequences. And whatever choice you make, it would have a consequence. Because if I do this, then I cannot do this. So I made that choice, not that I would have been qualified anyway. I'm not going to try to produce a gazillion papers or have the biggest research group or gain all the accolades that I want to gain. I mean, to me, that if they come, well, thank you, appreciate that. But to me, that wasn't important. And so you need to decide for yourself and also not compare yourself to others, right? Because your colleagues might make choices that would be fundamentally different from the choices that you would make. And I'm saying this especially for again, with the demands that we have with raising children, with raising a family, being a spouse, that takes a lot of work. That takes a lot of commitment. And so make choices, decide what you want, and go for it, knowing that you cannot achieve everything that you could possibly achieve, but you need to have both success as well as enjoyment, right? You could have success, but if you're not enjoying it, well, what's that success all about, right? Nothing. So have that aspect of enjoyment as well. And it's something, again, that could change in the long run, but it's these are choices that you need to continuously make. And I forgot the second question already, Manuel.
So the second one was related to the saturation of crop improvement.
Were there more details? Meaning, have we reached the selection limits, or I'm just
yeah, it was related. Can we get to a point that you get to that saturation? How can you tackle that? That was more or less the question.
Okay. In terms of selection limits, reminds me of a multiple choice question I gave in class. A selection limit is reached when, choice A, the breeder retires. In a way, that's a practical limit, right? When a breeder retires and that position is no longer filled, in a way, that's a selection limit, but that's not what you're talking about. I think the genetic gains differ in different species. Corn continues to be high. Wheat is a bit lower. Part of the lower selection gain in wheat is that for yield anyway, is that you need to maintain a certain level of protein for dough quality. And protein and yield are inversely correlated, right? So if you increase yield, that would come at the expense of protein. You want to maintain that, you cannot get as much yield. That being said, I think you could envision what changes in the environment might be needed. If you look at the Illinois long-term selection experiment for oil and protein, they got quite a bit of change just by changing the fertilizer that was applied. It's as if when they started applying fertilizer, you could think of genes that were not responsive, if you would, at the lower fertilization rate. Oh, suddenly they had a chance to be happy, so to speak, and express themselves. And they got more gain after that. So I think oftentimes or sometimes when we get to a plateau, we could think about P equals G plus E, but there's genotype by environment interaction. What can we do in changes to the environment? You can also think of, well, what fundamental changes can we make in the crop itself? A while back, I started working on dwarf corn at the University of Minnesota. Dwarf corn is corn that's about 2 to 3 feet tall. And we, instead of growing it 30-inch rows, we grow it 12 or 10-inch rows, kind of like growing corn, like a small grain. We abandoned that work, but now you hear of short corn from the different companies. So again, sometimes you need a major change. You might need a major change in the crop itself to get back on that gain curve that you would like. And there was a third question, Manuel.
Yes, the third question was, did you ever consider returning to the Philippines after your studies? And we have now a bunch of questions. If we have time, I can read those after.
Yes, I considered returning to the Philippines. I said I'd stay in the US for 3 years, could not land a job in the Philippines. So my wife and I made the decision that I would like to be the sole breadwinner, that my wife, we made that choice, would be staying at home, raising our children. I told her the work you're doing at home with our kids is far more important than any work that I could do outside of home. And yet we need to make a living. And so, but could not find a job. 3 years became 5, 5 became 10, 10 became 20. And then actually some recruitment came from the Philippines. But at that time it came to the point, you know what? Life situation, family situation, season of life does not make that change feasible. So the answer is yes, but timing does matter. And I've talked to enough people to know that that is actually a reality, that you may want a certain direction in your career, but there are other considerations that you would need to pay attention to, and timing also makes a difference.
Yeah. All right, I have 2 questions. The first one is, you talked about the future of land building, and I was just curious to know, do you ever say that in time in the future what would come where plant breeders will be able to breed crops that is sensitive to the environment, use GBI, where the plant that can grow in Brazil and also in the United States and all of that. That's the first question. And then the second question, you somehow talked part of it. I wanted to ask what is the non-scientific part of your life that I've kept research? like something outside of science.
Okay. Wow, loaded questions. Number one, no, I think G by E interaction will always be important because we can, yes, it's a pain, but we can also exploit it, right? It is advantageous for us. If I wanted something in corn, if I wanted a corn hybrid with zero G by E interaction, very easy to do. Breed corn that doesn't yield. Right? Zero G by interaction, bad product, right? So you think of G by E, it's a challenge, but it's also your friend that it can give you a better product or product placement in the end. Second, wow, what big themes I think have helped me in my career. For me, it's looking at what problems might need to be solved that are within my skill set. And I think of my career, it's been that. What are current problems that I see in the horizon that I can perhaps have a contribution given the skill set I have? And I found that as useful. A disadvantage of that is that I don't stay too long on a given topic. Because, this is a problem. I studied it. I published 2 papers. Okay, I'm done. I want to do something else. Even in the field of genome-wide prediction, I've spent a long time on it. I'm sick and tired of it, frankly. And I was sick and tired from the research perspective. Hey, I want to do something else. So again, it's just how I am. And I admire people who stick with a given substantial, meaningful topic for the entirety of a career. Cheryl, then in the back. Yeah.
I'm just curious, it might be different from people to people, but from your experience, was it difficult to move from, graduating from your PhD, moving to a private company, and then from private company going back to academia?
It had its challenges, but it was a fun process. First thing I learned when I moved from PhD to a private company is just, I thought I knew a lot of things, but no, that wasn't quite true. There's still a whole lot I had to learn. And then there's always an onboarding process in an organization. You need to know how things work, so to speak, in the new organization. It came to a reason I moved back to the academe. One was teaching. I moved to the academe. One was teaching, education, mentoring of students. And second, at that time in the industry, the only way, the path up, so to speak, was to go into research management, managing people, managing programs. And I didn't want to do that. I wasn't at that point in my career. And then the opportunity came up at Purdue. And so I decided to apply. And then decided it wasn't cold enough at Purdue, so I moved to Minnesota instead. Yes. But yes, each place that I worked with has been fun. I still remember, and it's fun to also see my former employers' progress. So the company I left at that time, their goal was to be in the top 10 in the US. One day we woke up, we're now in the top 10. How'd that happen? Well, 2 of the companies ahead of us merged, right? And then when I left the company, they became within the top 3. And I go, oh, maybe there's a cause and effect relationship to that. Rex is no longer around. Now we can go all the way up. Yes.
I have 2 questions. My first question is kind of like a part 1, part 2. So I guess 3 questions to total. My first question is about, you mentioned the technological innovations happening in the periphery of PhD, right? And it seems that, not just in PhD, but research and development, that industry innovations tend to be a few years ahead.
Mm-hmm.
So my question is, the current technology we're seeing right now, right? The rise of all these different advancements. What are things that you personally are excited about being adopted in PhD? And also, what are things that you believe in the future, maybe not right now, will be things that should be adopted?
Okay. Well, one thing I'm excited about is the use of artificial intelligence to make selection decisions, not as a substitute for a breeder, but actually as an aid for a breeder. And so I think, yeah, we can easily train machines in a way to replicate a breeder's decision. But beyond that, to help a breeder identify germplasm that the breeder might not necessarily select, but might have value, you know, that might have been missed, so to speak, and to identify those candidates. Maybe give this candidate a chance and don't discard it yet. So that's one aspect that is of interest to me. Another is designing breeding pipelines, right? If you think of a breeding program, it's a fixed amount of resources. We tend to study breeding in isolation. In the breeding courses that we take, okay, well, you cross parent one by parent two, you develop progeny and develop whatever, select whatever method. But it's much larger than that. There are questions, how many parents do I cross? How many progeny do I develop in each? How much emphasis do I put on genotyping versus phenotyping? And these questions that are extremely difficult to study in an analytical framework, but perhaps in a simulation framework, in a artificial intelligence, in a machine learning framework, I think they could be maybe not exact answers, but helpful answers to those sorts of questions in designing a breeding program. You're welcome. All right.
I was going to ask because I wrote a bunch of notes and I don't understand about it.
Use AI to figure out what you wrote.
So we mentioned the idea of looking at just not, if there's other objectives which have to do, it's not just the typical yield, right? Like you mentioned convenience with the Pokemon reference. With the shift in attention towards cost-effective sustainability and the idea of how do we address environmental variation, what do you believe will be the influence that will have in breeding? Or I guess, what would be our role? How would that affect our role as breeders?
It's a great question. Let me answer that two ways. One is even the criteria that we select for, right? So I'm in corn, and the criteria are yield and grain moisture and standability. For me, a more meaningful criterion would be dollars per acre. If I can breed for dollars per acre, looking at the profit that I would get and subtracting the cost of inputs, right? And whatever other offsets you might add to that, to me, that could be a worthwhile breeding objective. A lot more difficult to do than said because prices of commodities do vary. But in a way, if we think of it that way, it forces us to think more holistically rather than thinking of just one trait at a time. Second is perhaps we need to have a better appreciation of who are we breeding for, right? And a naive way of looking at it is we breed for the consumer. Well, that's a nice way of thinking about it, but how true is that? If I take coffee, for example, we think, oh, we'd like to breed for good tasting coffee. But really, if you're a coffee breeder, you're breeding more for the producer. You're looking more at disease resistance rather than taste in the end. Or even if you breed, say, for a certain taste or whatever profile, you could also think, well, does that translate to the consumer? You think of the different if you go to a supermarket, can you identify the varieties of what you're buying? Do you know if it's a Florida strawberry? Maybe you can. I don't know. I do know for apple, you can identify the variety of the apple, right? But you go beyond apple or say Bartlett pear or Anjou pear. Beyond that, you don't really know what variety you're consuming. And if that's the case without identity preservation, then the incentive, if you would, the impetus for breeding for certain consumer-friendly attributes becomes less. Just one thing to keep in mind.
Thank you.
We have a couple more questions online. If I may, I would like to read the next one. So it's in the context of what you said, having in mind the future. It says, in today's scenario and considering the future, what would you suggest new breeders who are starting a new breeding program? What are the main things to consider to establish a successful breeding program?
All right. What are the main things to consider in establishing a successful breeding program? For me, number one is germplasm. Germplasm. We as scientists, I think me included, tend to focus on methodologies and technologies. You know, that's the exciting stuff, so to speak. But you could think of breeding as a three-legged stool. You need breeding methodologies, you need good germplasm, and you need a good breeding team. Take any one leg of that stool and that stool falls. And I think it'll come to the point where the major breeding organizations or programs for a given species, they'd all be using the same procedures. There might be differences in scale and detail. And then all the breeding organizations, they would try to recruit the best minds, the best people. And what would differentiate them is the germplasm. And so don't forget that germplasm piece. If I were starting a breeding program, and I'm speaking a bit from experience because I'm helping start this leafy vegetable breeding program, it's our main challenge is finding a good germplasm. It's not easy to adapt African vegetables to Minnesota. Was there another question you said, Manuel?
Yes, there are a bunch, so just let me know and I'll keep reading them. The next one is...
Is the boss.
Okay.
Maybe one more question, and then we can save the questions for through a Word document and then figure out a way to get in touch with Dr. Bernardo, but we'll have to move forward.
Got it.
I can come again.
For sure. I also would encourage you to read some of the comments. All are very positive about your presentation. So the next question is, are we still using recurrent selection breeding? Yes.
Could you save those comments on the chat so at the very least I can, communicate with those people, folks asking questions? Are you able to do that?
Will do, sir. Yes.
Okay. Thank you.
So the question is, are we still using recurrent selection breeding programs for extracting and developing inbreds? That's
great question. The answer is mostly no, largely no, but I think we should. I think there's large value in a rapid cycle, short-term recurrent selection. Why do I say that? I did a study on distribution of outliers in the breeding program. When I say outliers, those individuals that are so far off the scale and that are very difficult to repeat. And the question was, well, are they difficult to repeat because they really are not repeatable, or are they difficult to repeat because the population sizes that we have are never too large enough to show that right tail on a consistent basis? And it was the second answer. Our population sizes are not large enough to consistently show outlier type performance. But what I found is that with a single cycle of recurrent selection, meaning you select, recombine, and select again, with a single cycle of recurrent selection with a few hundred individuals total, that beats having a population size of 10 million. You could grow a population of 10 million and select the best in one step, or grow small populations but do a recurrent selection type of thing. You get more progress that second way. Which means to say that I think there should be a place of recurrent selection in an inbred development program. The challenge, of course, is that takes time. But with things such as year-round nurseries, with speed breeding, if you're really in a hurry, you could even do embryo rescue. You rescue the embryos so that you do not go through the seed maturation process and the germination process. In some species, you could save time that way. But yes, I think recurrent selection idea introduced in the 1950s has gone by the wayside a little bit. We need to do it, but perhaps in a way different from what it was initially envisioned. All right.
Thank you so much.
You're welcome.
thank you everyone on Zoom for joining. We promise we'll save your questions and figure out a way to get back to them. Please stay in touch. The Plant Science Council and the Gulf Coast Student and Postdoc Association has a lot of online events. So follow us on social media. And yeah, thanks again for joining.
Thank you.
Okay. Manuel, I'm gonna log out now.